kernel methods such as SVM, etc., can be used for, well, we can use it for both classification and regression. The third answer, neither of the two, would not be correct. I believe most of you got this right, I would imagine. I wish I could see, a very good point, I wish I could see statistics here for each of the quiz.
Yeah, so yeah, with the Google one, like you see the question and then you see a pie chart, or you can configure how you want to visualize the result. And then there is a link. You click on the link and then it gives you the details, but without clicking on the link, you can see the visualization of how the class did.
Okay. So yeah, I'll look for it. Even my setup of Moodle is a few years old. I set it up in 2016. Most likely, I need to update it. So what is a kernel function? What does a kernel function do, guys? Remember that you have a mapping function that takes you to a higher dimension. And then you just take a dot product in the higher dimension. Right? So that's the way to look at it. First, each point goes to a higher dimension. And a kernel is essentially a dot product. A kernel function is a dot product in the higher dimension. Right? So if you look at it like that, you'll realize that none of the other things make sense. The function, the mapping function, is a function of only 1 point, not of 2 points. So this wouldn't make sense. This wouldn't make sense. Right? It is adding up the two vectors, so you won't get a number. You'll instead get a vector in the higher dimension. This is, well, funny, but not true. It's too complex. Then what do we do? It's basically a simple inner product in the higher dimension. Remember, that's the way I explained it to you. That's what a kernel is.
As if some people don't have the math background for that. So is there a way
you want me to re-explain that? Okay, let me do that. In fact, let me put it on the writing tablet and explain it once more. So let me do that. So the basic idea is that suppose you have data. Let's say that you have data, which is like our classic data was this. Let's take this egg-shaped data. And you have a data of another color, which was like,
yeah, that is your background actually.
That was exactly, that is it. And so we drew a decision boundary that would be like, let me make a thick one, a decision boundary that would be like, well, I'm not doing a very good job, but it's a circular sort of a decision boundary here. Now let's think about it. What are we trying to do? We are trying to go to a space. Let me go here. We are trying to go to a space. We are trying to find a function, right? Such that, if you remember, we can do one of many things. Either we can stay in the same dimensional space, but a point x, phi of x does what? So suppose you have a point x is equal to x1, x2, the coordinates of the two-dimensional coordinates of a point, x1 and x2. So without going to a higher dimension, one way you can do that is you can go to phi x is equal to x1 square, x2 square, isn't it? Do you see that, guys? Yeah. If I do this, then if you remember, the decision boundary became like this, and all the blue points were here, and all the yellow points then became here. So the game was to, first is that if you can find the phi, you are in luck. It's an explicit mapping function. Isn't it, guys? On the other hand, if you can't, then, well, it turns out that you don't really need to do that, so long as you can find the dot product in the higher space between 2 points. Right? So the kernel function, that is what it was. The kernel is a function given two vectors, x prime, what you do is, first you would do the inner product of it. You would first do x and phi x prime, right? So what would happen is, this is a measure. What is a dot product? Is the similarity between two vectors, right? It's sort of a measure. Inner product is a measure of similarity between two vectors, and so obviously these are also vectors. Maybe I should specify that x prime in the kernelized feature space, right? So it may be that you are taking 2 points. Let's say that this is x and this is x prime, right? As an example. So these two here, these are the two vectors, let us say. And then here, they will go to something else, let us say, right? x1, phi x and phi x prime. Something or the other, they'll go to two different places in the other space. And so this is the function that we use, the kernel function. We didn't go too much into the mathematics of this. I was actually planning to give you guys a session. If you want to understand how kernel functions lead to support vector machines and all of these solutions, kernel functions are beyond support vector machines. Support vector machines are just one very popular use case of kernel functions. If you guys want to understand kernel functions, let me know. If I get enough vote or enough asks for it, one of these Sundays I can make the seminar session and explanation of the kernel.
Yes, Asif. So, like if you can.
Yeah, let me do that. It's beautiful mathematics. Now that we are not doing the engineering math class, there wasn't enough enrollment for it. I suppose we should do it here.
Hey, one question, Sif. Regarding that, so if you go back to that note you were just drawing on the board, right?
You want me to go back to that? Huh? Okay, 1 second.
Yeah, so basically, so if you can see a circular boundary like that, like you had put like phi x is a vector x1 square and x2 square, right? But in cases where we cannot find a explicit boundary like that, then we just do like a, then how do I find this kernel function? Sorry,
That's
I
the
didn't.
beautiful thing. See, the beautiful thing about kernel function is, see, the normal story would have been that you have to first, step one would be, step one, without kernel trick. First is step one, find phi of x. That serves the purpose. What is the purpose? Of creating separable data sets, linearly separable classes. Then use it to solve the problem. Then solve the, essentially a maximal margin hyperplane problem, right?
Yes.
Max margin hyperplane that we already learned about, which is the hard or soft margin hyperplanes or classifiers. You can do that. But the point is, the main point here is that with kernel trick, that's the thing. And I didn't explain to you how, because that gets mathematically tricky. It has to do with something called the Mercer Theorem and so forth, that if this function is well behaved reasonably, then, and it generally is, if you take some good kernels, then you can actually need not learn the explicit form of phi x. You can instead solve the problem by essentially in some sense short circuiting. You can find phi x prime. You can find the inner product without actually knowing phi. Isn't that remarkable? And so if you can state your decision boundary in terms of just the dot products, you have a winner.
Oh, okay.
So there is a very beautiful intuition behind it. Well, I don't know. Is this okay? Very hand-waving argument, actually. Let me give you that hand-waving argument. Suppose you have 3 points, 2 points here, right? Now, if I ask you, I know that there is a point x whose dot product with this point. So this is vector. Let me call it x a. And let me call this vector xb, right? Suppose I tell you that I know some point, I know x a. I know this dot product and it happens to be 2. What can you tell about it? Right? You realize that, see, suppose I have a vector here, somewhere along this line. Suppose the answer is somewhere along this line. I can find a lot of points perpendicular to, I don't know, somehow you can find a lot of points that will satisfy this constraint, isn't it? That the dot product is equal to 2. Quite a few points you can find. But now I say its dot product with xb, it happens to be some number, let's say 6. Do you realize that that constrains me?
Yes.
Right? And so what you do is you end up picking up a unique value for x. There will be only one value of x that will satisfy this constraint, right? The more points that you add and you specify the dot product, let's say xc, I give you is equal to -4, something like this. What I have done is I haven't given you much choice. It is essentially triangulation, isn't it?
Right.
Right. So you'll be hard pressed to find a point which satisfies all of these conditions.
Yes.
And therefore, one way of specifying points in spaces, not by giving its explicit coordinates, which is that this one, it would be x1, x2, x3 component. Let me take an example, right? But alternatively, you can define x in terms of its dot product with respect to x dot product with respect to a set of points I, set of other vector points.
Yeah.
Right? It's an unusual way of doing it, but when you do that, the fact is, once you realize that you can do that, a whole set of magic becomes accessible to you. And that is what the kernel methods thing is pretty much all about. Cool. So let's go back to the quiz. So this question is now straightforward, isn't it? Let's go to the next question and see what we have here. This is something from the past. It was just a review question. I won't do this. This one, if x is a point in a p-dimensional space, arbitrary point, the kernel method for classification, a mapping function aims to do what? It wants to project it into a higher dimensional space in such a way that the two classes become linearly separable, right? The data of the two classes become linearly separable, right? And what do you want to do? You want to draw a hyperplane. So in two-dimensional, what is a linear hyperplane?
Line.
A line. In 3 dimension, it's a 2-dimensional plane. In 4 dimensions, it will be a 3-dimensional plane. So if you project data into a q-dimensional space, a hyperplane would be how many dimensions?
Oh, okay.
Q minus 1 dimension.
Yeah, that's the reason I was about to ask you like why it is -1. Yeah, okay.
That's right. That's the explanation. Well, kernels do not stand for Linux kernels or Windows kernel or whatever. In machine learning, kernel is the definition that we just went through. Next question, let x belong to RP. In the kernel method, the mapping function maps each point in the input feature space to a different point in the in the feature space, where the dimensionality of the other space is usually higher, right? Same or higher. So that's that. In this particular case, guys, what does the decision boundary look like? Linear, right? A
So
straight
Asif,
line.
when you say it is same or higher, so is that the same intuition as the neighborhood methods?
No, no. Look at this
That is
problem that we
separate.
just did. We just saw. So look at the background that I have. Do you notice that it goes to on the, when I look at it, do you see that it has
Oh.
gone from 2-dimension to 2-dimension itself? And
No,
if
so
you
I
remember,
think you're not sharing your screen. Other one.
okay, I will once again.
The background you are talking about, right?
Yeah, just the background. Do you see the background, the arrow from the left to the right?
Yeah.
So what am I doing? I'm separating it using this function, and you go from R2 to R2, plane to plane, isn't it? And if you remember the other projection I did, which is at the bottom of the page, if you go back and look at the video. In fact, let me see if I can find that video here, and I'll share it. And another thing here, neighborhood methods. If I have that visualization, kernels.
Yeah, that is a screenshot, like the bottom part of the screenshot.
Yes. So let me go back and share what I was going to share. This is a recap, guys, for you. Do you remember this? I could go from this. I don't know if you can see my mouse at all.
Yes.
Yeah. To
No,
this.
not mouse. Yeah.
Right. I could go from this to this, or I could go from this to this parabolic surface, isn't it? In the first case, I mapped from R2 to R2. In the second case, I mapped it to R3, three-dimensional space. Yeah. Are we getting it, guys? This image here is a three-dimensional surface, a paraboloid surface. Do you see that, guys?
Yes.
So your
Yes.
mapping function can be 2-dimension, 3-dimension. So in general, you go to a higher dimension, or at least stay in the same dimension. Quite often, you even go to infinite dimension if you use the Gaussian kernel. That's a bit of mathematics. We'll do it then, when we do engineering math. So the math of data science. So the math of data science, of course, had all of that fun stuff, the technicalities of it. So here, which kernels would work? A linear kernel would work or not? This is a linear decision boundary. So the linear will work, of course. A polynomial kernel will also work, because linear is an example of a polynomial. Degree 1. Will a Gaussian kernel work? Well, now you're projecting data into infinite dimensional space, but still, yes, it will work. In a simple problem like this, any of these kernels will work. What about this river data set? Will the different kernels work? Which kernel will work? Linear will not work because the decision boundary is certainly not linear. A polynomial will work, right? I'll leave that as an exercise for you. And a Gaussian kernel will work. In fact, let me show here. Where was I? This was SV river data set. Oh, yeah, here. Look at this. This is your data set. How do we go and do Gaussian kernel, with the kernel with radial basis functions? When I do that, the decision boundary is obviously very, very complicated here when you project it down. And this is how it is. It says that the river is red colored and so forth. So you can imagine that it has put all these lighthouses, the support vectors in these locations to identify the path. So that's what you do with this.
Does linear and does Gaussian and polynomial just work for mostly everything?
See, the question is, polynomial will not work for everything. If it is a transcendental decision function,
yeah, that's true.
Will be in a bit of trouble. Gaussian tends to work because you have expanded it into infinite number of basis functions.
Mm-hmm.
Polynomial in practical terms with high basis functions work, but then you risk overfitting. Gaussian there's a reason why Gaussian has become the most go-to thing. Trouble with Gaussian is it runs much slower than other ones because it's complex. So SVM, support vector machines and support vector regressors and all these kernel methods, they tend to run a bit slow. You need good hardware to run it.
Yeah.
And part of it is because you have to do. So if you can look at a problem and you can say that this is a linear problem, I can do it with linear, I can do it with polynomial, you converge faster. Another thing with support vectors is that don't take the entire data set, training data set or something. The computation will run for a very, very long time. Take a very small sample of the data set and try to run it, because SVMs get horrendously complex, like the computations when you have too many data points. So, okay, so what are support vectors for a data set with D features? The support vectors are, they're just some specific points, specific rows of data that act as support vectors. Those are the points that are either sitting on the maximal margin, on the margins or between the margins, the error points. Those are your support vectors. Going back to it. And this is just a mapping, the definitions. I hope most of you got this right. SVM is primarily used for unsupervised learning. Why did I say it's false?
Oh, it is supervised.
It is mostly used for classification regression. There is a twist. You can use it for clustering also, but it's a stretch. Right? Not that commonly used. A support vector machine is?
So if your question was support vector machine is used for unsupervised, then the answer would have been true.
For supervised.
No, so no, not instead of primarily what was not there. If it just says SVM is used for unsupervised learning, then it is true.
Can be used for, yeah. Then the answer can be used for would have been true.
Can be, okay.
A support vector machine is, what is it? Well, these three are correct. So this was a tricky one because out of the 5, 3 are correct. A classifier that uses the kernel trick to discover the support vectors without explicitly finding the mapping question. So Aditya, this is the main point with support vector machines. You don't have to explicitly find the mapping function. The other is it's an algorithm that conceptually maps the data to a different feature space where the instances of the two classes become linearly separable. True. A generalization of the soft margin classifier. Remember the soft margin classifier? We talked about it using the analogy of the river, the widest river we can flow. In a soft margin, we allow for some mistakes, some houseboats and some trees in the water. So the trouble is it only works for linear decision boundaries. I mean, linearly separated, separable classes. But then if you have data that's not linearly separable, then you have to project this data into a higher dimensional space using a mapping function where it will be. And in that space, now you can apply the kernel trick and solve the problem.
Yeah, Asif, just like on this, on your river example,
Right.
like one side houses and other side the trees where it floods.
Mm-hmm.
Actually, it is flooded right now.
Ah, right. Yeah, India.
Yeah, because of the yearly floods.
Right, we should take a picture. That's cool. Ganga is overflowing at this moment.
Yeah.
Okay, these are about, okay. So if there is some noise in the data sample, a soft margin classifier is likely to outperform the hard margin classifier if the data is linearly separable with respect to its classes. Why is this true, guys?
Oh, because of the budget.
Exactly, because you have some budget.
Budget and the constraint optimization problem.
That's right. Excellent. So then this is KNN. In this one, if the data looks like this, guys, which would be the best kernel to pick? Polynomial or Gaussian? Both will solve the problem. Linear won't, because you can't draw a straight line decision boundary here. So either two, in fact, polynomial kernel might converge faster. So these are old problems, KNN problems, and that is it, guys. I hope it was fun for you.